Hello, everyone. My name is Rubao, and I work for Rateup Incorporation in China. In this talk, I will present our paper titled as The Art of Balance, a RetubDB experience of building a CPU-GPU hybrid database product. In the past 2 decades, there have been a number of research papers about the GPU databases, and several industry GPU database products have been developed and deployed into real applications. However, the GPU database community still have several open questions unanswered. The first one is about algorithm choice. A whole GPU database system with multiple components can have a very large design space to select various algorithms. For example, join algorithms. It's unclear how a real product should adopt different algorithms. The second issue is that existing research work often focused on studying simple SQL queries represented by star schema benchmark queries. It's still unclear how fast a GPU database system can execute complex SQL queries. The third issue is that existing research work often studied query performance using read-only datasets without considering any co-running transactions. So it's an open question that when executing hybrid workloads, how a GPU database behaves and how to optimize such a system. Our purpose of this work is to answer those questions. To answer those questions, in this talk, I will first present an anatomy of RetubDB. Then I will present a performance evaluation using a standard complete TPC-H benchmark test. Finally, I will present the lessons we have learned. RetubDB is a hybrid database system that uses a CPU to execute transactions and uses GPU to execute queries. Its design and implementation is based on 3 balancing points, namely transaction versus query, performance versus engineering cost, and performance versus software portability. These points directly affected the architecture and algorithm choices in RetubDB. A fundamental problem for a database system is how it stores data. So considering the balance between transaction and query, RetubDB takes a dual store approach to separate the whole database into 2 parts. One is the alpha store, which is a primary read-only data store to serve queries. The other one is a delta store that records data modifications caused by transactions. Both stores are in a column store format, and a dynamic merging operation is needed to manage the 2 stores. This design has 2 benefits. First, it can minimize the interference between transactions and queries so that both the CPU and GPU can work independently. Second, it can let the development of the transaction engine and the query engine become relatively decoupled from each other. This is a very important benefit from the perspective of software engineering. When talking about query processing, here we only focus on how to execute the join operation. There has been a long history of debating on who is faster when comparing sort-based join and hash-based join in the past several decades. Ideally, a database should implement all the join algorithms and uses a cost model-based query optimizer that can dynamically choose the best join algorithm for a given query. However, we challenge this approach in RetubDB. When executing A join B, we first check whether one of the input tuples have unique values on their join key. Such a check can be easily done according to data schema information. If one has a unique value, we use hash join because the nature of unique values can greatly simplify the implementation of hash join using GPU devices. Furthermore, we check whether a star hash join operator can be used to execute a multiple join so that one table can probe multiple hash tables. If the unique value check failed, we use a sort merge join algorithm. In the merge step, we use the GPU merge path algorithm. For the sort part, we choose the sort algorithm according to the data type. I recommend the readers to study the merge path paper for details. This design is a result of balancing multiple factors. It can provide high performance for static gamma OLAP queries, and it can also handle any type of joins. More importantly, there is no complex query optimizer involved, and all the decisions are made by static rules. I quickly go through the transaction part and the memory part due to the time limit. Our transaction engine is a MVCC-based implementation. It's basically a combination of alpha store, delta store, delete vectors, and MVCC visibility check. The ultimate problem is how to balance the transaction on CPU and queries on GPU. Our general idea is trying to accelerate query executions while keeping transaction performance acceptable. Okay, memory management is also a balancing problem, considering that the source of evil in GPU database is actually the existence of two separate memories connected by a PCIe bus. Both manual memory management and CUDA managed memory facilities have pros and cons in different aspects. So RetupDB takes a hybrid approach to memory management. Now, I present RetupDB's TPC-H query performance compared to OmniSci with three kinds of summarized results. First, for queries with only single table aggregation, for example, query 1, OmniSci is more than 3 times faster than RetupDB. Second, for queries with joins, such as Q19, RetupDB is more than 3 times faster than OmniSci. And we also found some join-heavy queries cannot be finished by OmniSci. This result shows the advantage of our join algorithm choice. Finally, for queries with subquery features, OmniSci failed very often. And for the only one it can execute, Q18, RetupDB can have a 20 times speed up. Since there is no any GPU database system that have complete TPC-H results, we choose to compare RetupDB to 3 representative CPU database systems that have open published results on the TPC-H skill factor 100. RetupDB is the second fastest single node database system in the world. Although using one GPU card cannot let RetupDB outperform the action vector-wise single node system, using 2 GPU cards could do it. The results written in the paper still have a large improvement space, since RetupDB's fixed point arithmetic implementation is not optimized, which causes a Q1-like query cannot be quickly finished. I would like to present some insights and lessons we have learned using a fallacy and pitfall style. Fallacy 1, an algorithm's adoption only depends on its performance. This is wrong because other considerations are also important and even more. Fallacy 2, an HTAP database only needs a unified hybrid data format. But in our experience, a multi-stage data store approach can have advantage of decoupling components, which is a big software engineering benefit. And fallacy 3, a GPU database only depends on how to execute operations on GPU, but actually for certain queries, logic level optimizations are even more important. For example, the TPC-H query 21. So due to the time limit, I ignore the pitfalls. And our final conclusion is that the art of balance is a key principle to building a fully fledged database product running on CPU, GPU, hybrid hardware platforms. And thank you.